while we're waiting for everybody to join the lecture, if you like, you can go ahead and work on this problem. We'll be doing a lot of algebra today, lots of review. So you can go ahead and think about this. Okay, hello everybody. My name is William Ollis. Most of my students call me Professor Ron, so welcome to Pre-Calculus Math 2412, and this is section, let's see, I think this is 224. Check my notes here. I've got notes on top of notes. Yes, this is section 224. My previous section was 5, so let me make that correction. And your CRN for this course is, oh, I guess I should fix all of it. Sorry about that. I don't want you to think you're in the wrong class. This is 15672. Now, before we get started, I've got this problem up because we're going to do a lot of algebra today, but I want to just bring to mind some things that I need you to take care of. And let's see here. When it comes to, let's see here, let me move here, announcements. Okay. When I do my office hours, my conference hours, those will be for all of my students. And I've been sending out these messages to you, and you're probably tired of them, but that just means that I need a working Sanjak email. That is an official Sanjak email for you. When I go to Blackboard and I check send an email, I see all of your email addresses and they are your Sanjak email addresses. The only thing is you have to have activated it. That is, you have a password, you have claimed your account. So when I fill out the list, the recipient list for my conference hours, I must have workable Sanjak emails. I tried to do this on Sunday and probably anywhere from 10 to 15 were not valid. So Outlook basically tests your email to make sure that it's valid, that you have it set up. And if not, it's going to ask me to delete it. So I don't want that to happen. So if you're already using your Sanjak email, that's fine. For your WebAssign here, as you noticed here on the screen, I want your Sanjak email for WebAssign also. I know you have your Gmail. I've got Gmail. You've got Yahoo. You have Verizon, all kinds of email services. And that's fine. But in order to be able to get you information from the school and from me, I need your official Sanjak email. One good thing about the email is that the school will send information on a regular basis. You need to be hooked up with all of that so you get information that's important to you as a Sanjak student. So please do take care of that. And if you notice, everything in your Blackboard site is to help you. Maybe you've got more information than you need. The WebAssign is linked to the Blackboard so you can always activate and also access your WebAssign through Blackboard. They're linked. So I'm trying to make that easier for you. You have all kinds of resources here to help you out. So this class is actually going to be overload. You'll get probably more information than you actually need. But I'm very glad that you're here, and I'm excited that you're ready and willing to prepare for calculus. So let's go ahead and get started. Again, please take care of the email situation. If you're already good to go, then you don't need to hear me anymore, but I need a valid working Sanjak email. So let's go back to our screen. I have a Wacom tablet, and also this document camera just arrived yesterday from Japan. Last week, I was trying to find the document camera in the United States, and they just didn't exist. I think the earliest I would have been able to find one or get one was in October. So this actually arrived from Japan. So I'm glad for that. The technology has allowed us to be able to communicate well with our students. And this gives me a lot of flexibility. I use the tablet at sometimes, but this is actually the closest I could get to using an actual whiteboard. Now, what I want to do to get started is to focus on some ideas that are review, but to help you get more integrated into the notation of mathematics. So notice what I have here for the warm-up. I say factor the integer polynomial. Now, I'm going to give you Professor Ron's limit of factor this to give you some new ideas about factoring, but I want to show you some notation. We will use the Z. This is a common notation. WebAssign doesn't normally use it, but in the literature, you see this Z symbol here, and it denotes the integers. And you know the integers are the natural numbers, 0, and the negatives of the natural numbers. So I will often use this notation. You can say set of integers, but this is just a more compact way of saying it. Now, this little symbol here, element of, this just means this polynomial here is an element of the integer polynomials. Now, when we denote polynomials, we have the actual set for the coefficients and then the bracket x. So this just means set of integer polynomials. Set of integer polynomials. And that's, again, just a way to say we have an integer polynomial. Now, Some other notations that we will possibly use and that you'll use in calculus, sometimes we'll use the script R, and that will just denote the set of real numbers. So we can't list the real numbers, they're uncountably infinite, but a lot of times we'll say element of R, meaning a real number. Another notation will be a script Q for quotient, and this will just stand for the fractions, the rational numbers. Now you may have already used these notations in your previous class in college algebra. You may have even used them in high school in algebra 2. Notation like this is standard and very convenient. Now, and of course, the last thing that we're going to consider is the script C, which will mean complex numbers. The complex numbers contain all sets of numbers. So the complex include not only the real numbers, but also the imaginary. So include imaginary. So when we say a polynomial is an integer polynomial, since the integers are contained in all of these sets, it's really a real polynomial, it's a rational polynomial, and also a complex polynomial. Remember, when you say complex, you don't necessarily mean imaginary. You just mean that you're considering all possibilities. So a lot of times we'll focus this way just to get you thinking about integers. Now, when you look at this, this is indeed true. When we think about the coefficient here, 3, that's an integer. The coefficient of x is 1, that's an integer. And the constant term here, negative 14, is an integer. Now, here's what I want to do. I want to give you a little lemma that I actually use in my college algebra and pre-calculus courses to give you a more satisfying way to factor. Now, it doesn't mean that you have to leave out anything you've already learned before, but I want to give you some new ideas, and this is going to be called Professor Ron's lemma. And I'm going to write it in a notation so you can use this to teach your friends. So here's what we want to do. Consider the polynomial, and we're going to write this like in the standard quadratic form, ax squared plus bx plus c. And I want to give this a name. For now, we'll just call this p of x. I should have written that before, but I just want to give it a name, p of x. And this is going to be an integer polynomial, where, now again, all of our lectures will be recorded, and I will put up a link on our Blackboard site, which will actually post these on YouTube. The file sizes are fairly large, and so the best I can do is give you a link, and these will be up for you to review as you need. So here's what we want. The greatest common divisor, GCD, of A, B, and C is 1. What that means is that the largest positive divisor of A, B, and C is 1. That means they're called relatively prime. For instance, when you look at our polynomial here, 3, 1, and 14, the negative 14, the only positive divisor, integer divisor that they have in common is 1. Okay, so we call them relatively prime. The idea, ladies and gentlemen, is that if you have extra stuff here, like a common factor of 3 in all these coefficients, you factor it, because that's just extra baggage that gets in the way. So we always want to make sure that we have the relatively prime. That's important. Now, here's the theorem or the lemma. P of x, you have actually used this before, but I doubt you've ever written it this way. P of x factors in z in the integer polynomials if and only if. So this goes in two directions. There exist, and I'll write this out, integers. And when we say something factors as a quadratic, we can write it as two first degree term factors. There exist integers z and w such that, and this is the little algebra that you always do when you do these kinds of problems. Number one, AC equals ZW. So that's what gets the ball rolling. That's how you start the process. That's what we call it the AC lemma. And this is the number theoretic part that we must hold if the integer polynomial factors. This will be, in this particular case, the B, that is the coefficient of X, or the linear term, must be the sum of Z and W. Now, what I want you to do is just take your red pen and put a box around these two. These are the two restrictions that must occur when we're doing these kinds of problems. We know that if we can find a Z and a W, then we're in good shape. Now here's what's important. The Z and the W are not unique. They are not unique. So when you're working a problem, you may come up with different numbers, or you may, for instance, like I'm saying, your friend might call Z your W, and you call your W their Z. So the interchange and all of that will not matter. So the uniqueness is not something we have to worry about. But the thing is that normally what we'll do, whatever two numbers you find, your friend will find also, but maybe out of order. So here's what we'll do. Let's go ahead and look at this polynomial and apply this lemma to give you an extra insight into how we factor quadratic polynomials. So now notice, for our warm-up, we have A equals 3, we have B equals 1, and we have C equals -14, kind of like we're doing the quadratic formula, which you're very accustomed to doing. So now AC equals 3 times the -14. Now, the idea here is we can go ahead and check 2 just to see if we hit the jackpot. But notice here, when we add these two numbers, we get -11, and that's clearly not 1. So what we need to do is factor the 14 to see if we can find better candidates, or candidates at all. So let's go ahead and factor. So we have 3. And then we can write this as a -2 times a 7. Just break that up. Use parentheses if you want. Now what we can see here, this is the part where you put the numbers together in a way that gets you where you want to go. So you can see by breaking up this number, we've got a valid path here. Now let me just tell you one thing. Sometimes this part will take more time. It will take a little bit more trial and error before you can get to a Z and a W that actually work. And if you can't actually find one, or find a pair, then it doesn't factor, which again, you're thinking you'll just use the discriminant. But sometimes it's really nice to have a factored equation based upon this method, because it makes the work a little bit easier to access. So now let's go ahead and put these two together. That gives us a -6 and a 7. So when we look here, when we sum these two numbers, say for instance, we let Z equal -6 just based on the theorem, and W equals 7, then the sum of those is actually the coefficient B. So this would work. So now at this point, all we have to do is factor by grouping. So now we take our polynomial 3x squared plus x minus 14. And now the whole idea with this Z plus W is we use these numbers to rewrite the middle term, so to speak. So we have 3x squared minus 6x plus 7x minus 14. Now, at this point, your old friend factoring by grouping will step in. That is, now that we have this written in this particular way, and students say, well, what about the order? Well, sometimes we want to put the order and group these in a way that gives us the most power, and this will give us more factoring power. So for instance, now when the first two terms are considered, we have a common factor of 3x. So we get an x minus a 2. And then in the second two terms, we have a common factor of 7. And again, that leaves us an x minus 2. So we'll know that we've done all of our computations correctly when we see that we have the common factor in both expressions. And then, of course, by the distributive law, which is what factoring is, we just have x minus 2, which is multiplying the 3x and the positive 7. And we are done. So when I do my Smart Pen videos, the last thing I say in the videos is, and we are done, meaning that we've accomplished the task that's been asked of us. Now, I just want to make a point here. How you decide to factor integer polynomials is completely up to you. And I'm sure most of you have techniques that you've used since high school. The one thing that's nice about this particular format here is that it is something that you can explain. You might have a friend that says, how do you factor? I can't factor for some reason. I don't have the knack to factor. Well, show them that it is number theoretic, that you check the product of AC. And what you do is you look for factors that equal this product whose sum is the coefficient of the linear term. Now that sounds more technical, but if you write these equations down and show them how you manipulate them, then it becomes much more of a straightforward task. Many students will ask, you know, is there a way to describe this so I can actually understand it? And I say exactly. The thing about mathematics is that many processes can be explained efficiently. Now, intuition, which we all have and enjoy, that can be something that some individuals might have more of in a particular field than others. Maybe they have more talent and think intuitively about structures in engineering. Maybe students think more intuitively about theoretical ideas. All of us have different attributes, but the idea here is that I don't want you to struggle with factoring, and I want you to have a clean, efficient way to do this. So you can add this to what you already do in your work and be happy that when all is said and done, that you have a neat way to do things and a clean way to do them. Now, what I want to do is give you some formulas that turn out to be very useful. When we do factoring, and these are in your book, I just sketched these out. These are right out of your textbook. And what I've done here is the book actually breaks them down into two categories. This category here is just basically the binomial theorem, and a lot of these flipped around. So there's not a whole lot new between the two columns. But when we're doing work in mathematics, there are formulas that actually help us out that are very convenient. That is, the first factoring formula here, which you learned in Algebra 1, is the difference of two squares. Again, you know this, and in this particular text, they use A and B uppercase as the variables. You can use any letters you like. It doesn't matter. Sometimes the A's and B's are easier to see. Some students like to use lowercase a and b, or even X and Y. It doesn't matter. This is basically what Dr. Stewart does as he's written his book. And a lot of times in trigonometry, I'll use A's and B's for arguments of trig functions because they're easy to see. Now, the first one we've lived with. And what I wrote here this morning, I asked my students, I said, ladies and gentlemen, what is an identity? Because what you notice is that these are all equations. And all we're assuming in this particular case is that A and B are real numbers or real expressions. And anyway, they could actually be complex numbers. It wouldn't matter. So for now, we could just say that A and B are real expressions. And the interesting thing about all of this is that we don't even have to restrict to that. We can even use complex numbers. The expressions can be complex. We just won't have as much time to deal with these, but we can have that. These are equations. If you look here, an identity is an equation that is true for all values of the variables for which it is defined. So that means that as long as these equations are defined for A and B, then it's true. You can write A squared minus B squared as A minus B times A plus B. Again, this is an identity you have known for a long time. Now, two other identities which you used in college algebra, again, we notice that when we have products here, if we're solving equations, the zero product law is very useful here, because when we set things to zero, we can set each factor to zero. So factoring does really assist us in a major way. The 2 and 3 are identities that we use, but maybe aren't as easy to remember. We have the difference of 2 cubes, and we have the sum of 2 cubes. So for instance, A cubed minus B cubed will be A minus B times A squared plus AB plus B squared. I want you to know these. Now, how do you prove them? Well, you multiply it. Use the distributed law. Again, brute force. Number 3 is A cubed plus B cubed. Now, these formulas are related. The only thing is that we interchange the plus and minus between the two equations. For the sum of cubes, we have A plus B times A squared minus AB plus B squared. So again, these formulas you really do need to put on a note card and practice writing them so that you actually know them. Now, 4 and 5, I'm sure you learned in Algebra 1. These are called the perfect squares. What it basically says is that you can write these two trinomials, so to speak, as a perfect square. These formulas are easy to remember, and you're thinking that's kind of like the Professor Ron's lemma. If I forgot these formulas, I could still use Professor Ron's lemma to work this out. We would just get two factors that were the same. So these are the very common A squared plus 2AB plus B squared equals A plus B quantity squared, the perfect square. And then A squared minus 2AB plus B squared equals A minus B quantity squared. So my thought here is that these are somewhat easy to spot, but if you don't spot them, you can still factor by Professor Ron's AC lemma. They're just convenient, and we like convenience. Now, notice with the products here, we've just basically turned 1, 4, and 5 around for 1, 2, and 3 here. So that's nothing new. That's just looking at these identities differently, where often, you know, we use an identity and we think of the left-hand side always being A squared minus B squared. But what if we have this? It's also important to recognize that we can go in the opposite direction. That is, if we have A plus B times A minus B, maybe it would be more convenient to write it as A squared minus B squared based upon what the problem is asking us to do. So the idea is there are many, many uses for these identities. And we will be working a problem and see that, well, it's convenient to think of it in these orders. Now, again, we flip 4 and 5 around and get these products. And then you're thinking, that's just squaring the binomial A plus B and squaring the binomial A minus B, which we can easily do. Now, 4 and 5, what I've written here, binomial theorem. When we get to the end of the class, ladies and gentlemen, we will have a more generalized version of these called the binomial theorem for the integer powers here, the positive integer powers. And I'm going to show you a way to generate coefficients when the powers get larger. Now, the one thing that is good to do here is just to maybe prove one of these and just do it by the proof of brute force, so to speak. Now, if we have the binomial theorem, we would actually know what to write here. Notice this little triangle here that I've written. This is actually Pascal's triangle, which generates these coefficients. Notice here, the 1, 2, 1 gives you the 1, 2, 1 here. And the 1, 3, 3, 1 gives you the 1, 3, 3, 1 here, even though if you have negatives here, the signs can alternate. But the idea here is that there's a lot of theory going on here, but maybe sometimes we don't need all of that. Maybe these are the only formulas that are useful to us at this point in time. So what I want to do is say you have a friend you're tutoring and they ask, you know, how would I prove this formula? Well, let's just do it by standard algebra. And this will just give us some practice in collecting terms and multiplying things, which we really get rusty on pretty fast. So we're going to say proof, just because we want to practice the distributive law. So we're going to say our left-hand side is A minus B quantity cubed, okay? So when we do that, we're thinking, okay, well, what does this mean? If we have x cubed, that just means x times x times x. So let's just replace x with a minus b. So this is a minus b, very simple, but very useful. A minus b times a minus b. So we see that our notation for mathematics here is very convenient. It's often we prefer to write this. When you solve equations or solve polynomials, maybe this is more useful, depending on what the problem asks you to do. Now, what we want to do is use the associative law, because now we've got to decide which ones are we going to multiply first. So let's just use brackets, and we'll say a minus b times a minus b. And then times another a minus b. So with the associative law, what we're saying is we're going to do this first and then multiply here. So you can associate however you want. So now let's go ahead and multiply this out. Notice we're going to have it multiply the a minus b times the a first. So a times a minus b. And now multiply a minus b by negative b. There are all kinds of ways to write this. It's not unique. So don't think that if you don't do it exactly like Professor Ron, it's no good. You use your methods. Just be careful to do legitimate mathematics. Okay, so again, by the distributive law, this equals a times a minus b plus a negative b times a minus b. So now let's go ahead and multiply this out. This will be a squared minus ab, and now we have a minus ba, which we can still write as ab because real numbers commute or complex numbers commute. And then what negative b times negative b? We all know that the additive inverse times the additive inverse is the positive. So this gives us plus b squared. All right. And now we're thinking, well, that's just the perfect square anyway, so maybe we could have used the formula. But I'm not using any shortcuts here. We're just going to do this the old-fashioned way. So now we can combine some terms here. Again, this is the perfect square, so to speak. So this is a squared minus 2ab plus b squared. So you're thinking, we could have just used the identity on the previous page, and if you did that, that's fine. I just want us to get some practice looking at everything from a very foundational standpoint. And now, of course, we multiply by a minus b. Now, the last step is to say we multiply this by the a, and we multiply this by the b. So let's write it as a times a squared minus 2ab plus b squared, and then minus the b times a squared minus 2ab plus b squared. You're thinking, I'd prefer the binomial theorem because this is a lot of work. Now let's go ahead and multiply through. Again, we keep using the distributive law. So now we have a times a squared, a cubed, a times the negative 2ab, so that's negative 2a squared b, a times b squared plus a times b squared. Now let's move to the second expression. So we have the negative b times the a squared. So we'll just do it in alphabetical order. Do the a squared first. And then negative negative, that'll be a positive, plus 2ab squared. We use that as a theorem. It is a theorem and it's very useful. Negative b times the b squared is negative b cubed. So remember, when we say negative 1 times negative 1 equal 1, this is a theorem. We proved that. But of course, when we say AB equals BA, that's just an axiom. That's a result that we assume about real numbers. We don't prove that, we just assume it because it makes sense to do so. Now we just want to collect our terms. Now notice a cubed is only one of those, but the a squared b, we've got two a squared b with negatives. We've got one here and one here. So that's going to be a minus 3a squared b. So we check that off, that's checked off, that's checked off. And now the ab squared term, we've got three of those. So 3a, and the order here doesn't matter. Doesn't matter what order you write these in, it's your choice. Then minus, so that's gone. And then minus b cubed. So what I did is I wrote this in the same order as the formulas on the previous page, but notice a pattern about this. This is really not hard to remember. And I'll just say, well, this is the right-hand side. So we're done. We've done the proof, so to speak. Now, notice that 3, 2 plus 1, 3. 1 plus 2, 3. When we look at the sum of the powers of A and B, they're always 3. So that makes this easy to remember. We just have to remember the 1, 3, 3, 1, and the fact that we have a minus B, we get the negative here and the negative here. So when it comes to remembering this formula, it's really not so bad, but this is what we call just a standard, straightforward algebraic proof, just multiplying everything out using the distributive law, using commutativity, and using associativity. So again, this kind of problem just reminds you about collecting terms and doing basic algebra. And my friends, there's nothing wrong with that. Basic algebra is good for you. Okay, now let's go ahead and look at an example with the difference of cubes. Now, so we're done with this. I just wanted to show you that we don't have to just believe everything. We can actually prove things. Now, here's another example that I want you to factor where we can use one of our formulas. We have a cubed minus b to the 12. Now, what we're asked to do is factor. Now, when we factor this, we first look up here and say, well, this is not this. This is not a binomial cubed. This is a binomial expression, but it's not raised to any power except 1. So when we look at this, we think difference of cubes. That's all the patterns we have, difference of 2 cubes. Now, not all problems in algebra are important to us, but we practice algebra so that we can do it when we need it. So now what we're going to try to do is write both of these as cubes. This is already a cube, but we know that 12 is 3 times 4. So we're going to say that a cubed minus b to the 12th can be written as this difference of 2 cubes. So a cubed minus, now we'll have b to the 4th using the laws of exponents, cubed. So remember, 12 equals 3 times 4. Here, let me put that up so it looks like a times instead of a decimal. 3 times 4. So we can use the laws of exponents here, 3 times 4, to rewrite the b to the 12th. And now we see we have the difference of two cubes. So we can use our formula to say that uppercase A is just lowercase a, and uppercase B is B to the fourth. And now we can use our formula. Let's remind ourselves, A cubed minus B cubed. Until you get used to these, you really need to write them down. We'll have A minus B times A squared plus AB plus B squared. Okay? So now all we have to do is fill it in. That is, now for A, we'll replace it with lowercase a, and for B, we'll place it with B to the fourth. Now, what's important here, and that we know in mathematics, is that not only do we recognize patterns, but we also use deductive reasoning to make sure that whatever pattern we see, that it's consistent with good mathematics. So now we can do what? A minus B to the fourth. Now we need to square A, so that's lowercase a squared. And then we need plus AB, so this will be A times B to the fourth. Then plus squaring the B, so that's the 2 times the 4 gives us B to the 8. So now when we look at this, though this is not very glamorous, you're thinking, why do I need to know how to do this? Well, you may find instances where noticing the pattern of the difference of cubes helps you to solve equations and to find all solutions. So notice, writing this expression as a product is a step forward. It's improving the mathematics when it comes to solving equations, which I'm sure you remember in your college algebra course. So good for us. Now, so what we're seeing is that maybe this seems a little bit dry and you're thinking, wow, you know, I can't wait for calculus. But my friends, let me tell you this. You spend the time in this class to get really good with your algebra and your trigonometry and get really confident making good choices with your math. Then when you get to calculus, you have all of the raw material to navigate the problems. So when you see difficult equations, when you see trig functions, when you see domains of functions, when you see logarithms, you know what to do, and you're going to learn even more about the functions in calculus. You think you know a lot now, you're going to even learn more in those classes. So that's what you have to look forward to. Now, what I want to do is share with you some more factoring techniques. Now, I had a student ask me about this problem, and this will be something that we'll use quite a bit in calculus. I remember telling the student that I said, this is a good calculus technique. So what we're going to do is look at this example. It's a Webasine example. So we have 6x to the negative 1/2 plus 5x to the 1/2 plus x to the 3/2. Now, you're thinking, that doesn't look like Professor Ron's lemma, but here's what the instructions are. Factor. Sometimes you have to factor by grouping. Sometimes you have to factor because you're aware of a technique that reminds you of an identity, so you rig it so you can use the identity. That's why most students don't like factoring. It's not always very straightforward. Now, let me give you a trick here. You're noticing, you're thinking, well, Professor Ron, I could move that x to the negative 1/2 into the denominator and then get a common denominator. And you know what I'd say? You're exactly right. You're exactly right. We're going to do the same thing, but I want to show you a technique that might be a little bit easier to do, but it's your choice. So to start this problem, we're going to factor. Here's the technique. You'll use this later. The least power of x. That's the strategy. So this is the strategy. When you have expressions that are common throughout a sum to varying powers, and you want to simplify it, try factoring the least power. Notice here the least power, well, it looks like -1/2. So in this case, it is -1/2. So that's what we're going to do. Now I want to show you a little trick here so this doesn't seem so crazy. Notice first 6, 5, and 1, they're all relatively prime. So we don't have anything to do there. But notice x to the 1/2 can be written as a product with x to the -1/2 in it. Just do a little bit of algebra. -1/2 times x to the 1, or just x. Those are equal. But it has an x to the -1/2 in it. X to the 3/2 is really, or can be written x to the -1/2 times x squared. So the idea here is you can always put in the x to the -1/2 and accommodate for it. And write it so that these terms have the x to the -1/2 in them. So this is a trick that the first time you see seems a little bit odd, but now you can see we can do it. So we have x to the -1/2. So now we've removed that. So what's left behind is 6. That was easy. And now, of course, we have the 5. And we see if we remove the x to the -1/2, we have the x left over. So don't just guess. Just when you multiply these together, -1/2 plus 1 gives you x to the 1/2 and then the 5, so that checks out. And then for the last one, we've got a 1, so we're just going to have an x squared. So now look at this algebraic manipulation here. When we multiply through by x to the -1/2, we get exactly the original equation. But now we've got a simple quadratic, so I'm going to write it in descending order. X squared plus 5x plus 6 times x to the -1/2. Now, we don't even need Professor Ron's lemma for that. That's the easiest to factor ever. That is 1 times 6. If we, let's just say you're teaching someone, you say, okay, 1 times 6. And then you say, well, 1 plus 6 equals 7. That's no good. So we pretty much ignore obviously the 1. So we just look at the 6 and say this is just 2 times 3. So you can actually do that in your head. And of course, 2 plus 3 equals 5. So this doesn't even require factoring by grouping, since it's the leading coefficient is 1. We call that a monic polynomial. And now what we can do is write this as 1 over x to the 1/2 to get rid of the negative power, just to make it look a little neater. And now if you want, you can just kind of move it downstairs as a fraction. So we have x plus 2 times x plus 3, and we can get a little bit more elaborate and write the 1/2 as the square root of x, like that. So you look at that and you look at this and you say, well, that's really complicated. This is very nice. Factor everything in one piece, one unit. So what we're seeing here in this particular problem, though we had to factor the quadratic, we only found the quadratic by using this technique here. Again, if you took the x to the -1/2 downstairs and did the common denominator approach, you would get the same terms here, exactly the same terms. And that is not an issue whatsoever. But this kind of gets you to the punchline in the same amount of steps. And maybe once you get used to it, is a little bit easier. So I'm thinking that as I have taught calculus over the years, students tend to really like this technique. Once they get used to it, it becomes something they do on a regular basis. So think about this as you're doing your web assign. I think you'll find it to be kind of interesting. Now, I want to do another factoring problem that's just like this. It basically doesn't, say, okay, factor this. What does that mean? Well, first, like when we looked here, we looked for common factors. And we thought, well, we don't really have any common factors unless we think about it like this. Well, let me just give you an example where all we have to do is some house cleaning, where the factors are kind of obvious to us. So for instance, we have 5 times x squared plus 2 to the 4th power times the 2x times an x minus 2 to the 4th. That's the first term, plus x squared plus 2 to the 5th power times the 4. We just kind of squeeze the 4 in there, and we have an x minus 2 to the 3rd. Now, again, 5 times x squared plus 2 to the 4th power times 2x times x minus 2 to the 4th power plus x squared plus 2 to the 5th power times 4 times an x minus 2 raised to the 3rd power, and we're asked to factor this. Now, if you think about this problem, it's just really much like the last one, but even easier. But still, there's work to be done. We think if we factor this, we want to remove the common factors from each of these. So the first thing we want to do is just, again, start looking here. We don't have a 5 over here, so that 5 is going to stick around, but we do have x squared plus 2 here and here. We have 4 copies common to both. So that's the first thing we're going to take out, x squared plus 2 to the 4th power. So I'm just going to go ahead and write the 5 as 4 plus 1. And so now we've gotten rid of this and we've gotten rid of that, but that one's still hanging around. And now we look a little bit closer. Well, we do have a 2 because that's a 2 times a 2, right? So we have 2 times 2. So we can get rid of the 2 here and one of the 2's there. So always use check marks. Don't use slash marks. The slash marks are no good, so please don't use them. Okay, that x stays because we don't have an x here. But now if we look at x minus 2, we've got 3 copies in both. So let's go ahead and extract those. This is just a way to keep up with what you've done. Now, of course, right, the 4 is a 3 plus a 1. And so now we have that taken care of, and that one's gone. So now when we put our bracket here, we just remember what we didn't take out. So now when we look at this, we go here and we see we have a 5. So we need the 5. And we look through here, the x was not extracted, so we have an x. And then, of course, 1 copy of the x minus 2 was left behind. So if you maybe put little checks or whatever just to remind you what was factored, you can easily see what you didn't factor. Now, we look here. Notice here, we've got rid of all of these factors except 1, so we have an x squared plus 2. And then of the 4, we only took the 2 factors, so we have times the 2. And then, of course, the x minus 2 to the 3rd, we got rid of all of that. So that's a way just to kind of do some bookkeeping. Now, of course, you could have said, well, Professor Ryan, that's hard for me to see. You could have just written this as x minus 2 to the 3rd times x minus 2 and broken it up a little bit more, and that's certainly fine too. I'm just trying to show you a way to actually do that, maybe with less lines of work. But any method is good. Just have a way to keep up with what you've actually extracted. And so now we're good to go. So we have 2 times x squared plus 2 to the 4th times x minus 2 to the 3rd. And now here, let's see what we have left. 5x times x, that'll be 5x squared. 5x times the negative 2, negative 10x, good old distributive law. 2 times x squared, 2x squared. And then 2 times 2 gives us a 4. Now when we look at this, we're good to go. All these are equals. Sorry, I left out my equals. We need equal signs. We need good notation. We don't want to have our reader read our mind, so to speak. So this gives us 2 times x squared plus 2 to the 4th, x minus 2 to the 3rd. And now we can combine everything. We have the 5 and the 2, 7x squared. We have the negative 10x, and then we have the plus 4. Now, of course, this was not a difficult problem. Mainly what I want you to see here is that this is just a review of greatest common factor technique. Extract the largest power of all the common factors, the greatest common factor, and then we have a nice, neat product. Notice this sum is now a product, easier to analyze. So again, a little bit dry, but when you're doing a calculus problem, this might be what you have to do to complete it. Students are happy as long as they don't have to do a lot of algebra, but trust me, the algebra does eventually get into the picture and in a way that's really very tedious. So the idea here is that the tedium is not what we always want. It just turns out that we can't avoid it. And if we don't practice the tedium, then the tedium takes over, and we don't want that. Okay, so now, ladies and gentlemen, I do want you to look at the very last problem in the WebAssign in 1.3 and think about that. I've got a little note here. I'm going to say more about this. I've done some formulas here, and as I was looking here, here's the formula that I'm talking about, which I want you to come up with. The idea is that there are special fourth degree polynomials that we can factor. And I like the WebAssign problem. It says, okay, think about this and look at this technique and how you can actually factor a fourth degree polynomial that's monic, and you might not have thought about this. So I want you to look at that, and I'm going to test you on it tomorrow just as a warm-up. So keep that in mind. That's just to keep you interested. Now, what we have when it comes to doing lots of algebra, like we just talked about, we've got plenty of factoring problems, but we also have to deal, like I said before when I was talking about the negative powers, we have to deal with a lot of fractions. We have to get common denominators. We have to divide by fractions. Fractions are in the story. So what we want to do is to review, this is in 1.4, we want to review some rational expressions or fractional algebra. This is what you spend a lot of time on in intermediate algebra. The idea here is these types of techniques get a little bit rusty. Even if you've had college algebra, these techniques tend to not stay with you as maybe they should. And so we want to review some of this. So the very first one is just to remember that when we deal with fractions, for instance, here's a common rule. This is the definition of division. That is, if we have A over B as a fraction divided by C over D, we must define division in terms of multiplication. And what that means is that if we're dividing a fraction by a fraction, we invert and multiply. That is, we have A over B times D over C. So when you think about this and you think intuitively about this, this is the only definition that's possible. I mean, for instance, if we have 3/4 divided by 1/2, if you think about this intuitively, well, in this case, 1/2 is smaller than 3/4. So if we divide it by 1/2, we're going to get something bigger. So we can't do that unless we think in terms of the definition. So this is 3/4 times 2 over 1. And now, of course, we can think of this as 2 times 2 times 2 over 1. These two of the 2's absorb, and we're left with 3/2. So if you divide 3/4 by 1/2, you get a larger number 3 has. So what I want you to get used to doing is to like thinking of like putting a box around things or putting checks by them. Don't put slash lines through them. If you slash all of your work, how can you read it? I think that's just become a habit that really is not good. It is better to write things in a way where you can clearly go back and see that these absorbed. I don't usually use the word cancel, I'll say absorbed, and you can check your work and make sure that it makes sense. So even though I know you know this, this is very important. This is a definition. It is not a theorem. It's like commutativity or associativity. So let's do an example of this. So when we look at this particular problem, let's just say we want to simplify. Simplify. So we're going to have x plus 1 divided by 9x squared. So now we get to use our definition of division. And multiplication's easy. You just go across. That's not something that's difficult. It's the division that gives us trouble. Divided by x squared plus 2x plus 1. We look at that and say we recognize that pattern from the factoring formulas. And then 3x squared plus 2x minus 8. Now, lots of times what I'll do is I'll refer to notes, or maybe I'll refer to WebAssign problems, and I want you to feel comfortable with the WebAssign, and I want you to do it consistently and meet the due date so you can maximize your homework score and your quiz scores. Now, first off, if we look at this problem, we're thinking, well, notice here, this is a difference of 2 squares. So first we can write it, each of these terms as squares, and then we can interpret the division symbol, which means invert and multiply. So let's do that first. So 9x squared is just 3x squared, and 16 squared is just 4 squared. Now let's go ahead, invert and multiply. Don't try to do all the steps at once, do them one at a time. So now the 3x squared plus 2x minus 8. And there are many ways to write this. We could do this as a complex fraction. We could just say a slash line and then the fraction. It means the same thing. So be flexible. Just remember, for instance, let me give you another way to write this, just as a little aside. A divided by B divided by C divided by D. We could also write this way. A over B divided by C over D. That's a common way to write things in mathematics and physics. So this notation is used, but this is actually even more popular. And so then we could say this is just AD divided by BC. That's a very popular notation. So get used to seeing it this way also. And in calculus, this occurs all the time. So now we have x squared plus 2x plus 1. Now, we know the formula for a difference of 2 squares, and if you look closely at this, you know that's a perfect square. That's just x plus 1 quantity squared, because we have the a squared plus 2ab plus b squared, where the a is the x and the b is the 1. That's easy to see, but even if you didn't see it, it would be simple to factor. But this is Professor Ron's lemma right here. So let's do a little aside. So for the part up here, we see AC equals 3 times. So we do a little sidebar so we know how to fit it into the problem. And so now we look at this and say, okay, well, if I add 3 and -8, I get -5, and that's not 2, so I need to work a little harder. So let's break it down some. So we have a -2 and a 4. And then we look at this and say, well, that might be a little bit better if we think about this as saying, okay, well, notice we've got a -24. And here, if we think about, say, a 6 and a 4, oh, that's going to give us a 2 here. Now, where's the negative go? Well, we're going to need to put the negative with the 4. So we'll say 3 times 2 times the negative 4. And then this will just be 6 times negative 4. Now, of course, how much time you spend on this is up to you. I think if you're teaching someone, you take your time, but you can say, oh, that's negative 24. I'll just use 6 and negative 4. Boom, I'm done. Well, again, as you work through this, note that usually the numbers will present themselves easily. But I want you to be able to do this when the numbers aren't so user-friendly. So you have to work a little bit harder, break it down and see, well, how can I combine these so this will work? So now there's a check there, so we can move forward. Now notice we're going to have a minus b times a plus b. So this will be 3x minus 4 times 3x plus 4. Wow. See, that good old difference of 2 squares, our friend. We never forget that. That's just useful. Now we can factor by grouping. But of course this, the denominator, that's just the perfect square. That's x plus 1 squared. And we see we're going to get duplication there. So that's going to be something that will absorb. And now we can do 3x squared. Rewrite the middle term, plus 6x minus 4x minus 8. You want your work to be neat, okay? And you don't want it to be haphazard. So as you're working the problem, if you need some side calculation, do it. And then move back to the proper problem. Okay, so now we've got x plus 1. We won't absorb yet. Let's just go ahead and wait on that so we can make the problem neat. What order you use is up to you, obviously. And so now we can factor here the 3x. So let's do that. So that gives us a 3x. And we leave an x plus what, 2. And of course here we can factor a negative 4. Just looking for the greatest common factor. Now, it's easy to slip up. Always go back and check and make sure, okay, that gives us that. So we've got that common factor of x plus 2. So that looks good. And now we're pretty much done. We'll factor one more time, and then we'll be good to go. So now notice we have an x plus 2 and everything. So this is x plus 2, which multiplies the 3x and the negative 4. And then, of course, we have the x plus 1 quantity squared. Now, this is where we can say, okay, well, and you know what? Let's go ahead and do this. This is what I said before. Some of you may not like me breaking up the power. So let's just write this as x plus 1 times x plus 1. So now what we can do is just say absorb. I would prefer that you do this instead of slashing through it. I know that's going to be hard for some of you, but you'll get over it. And then we have 3x minus 4 and 3x minus 4. Or we can write them so that we can align them. That's an extra step, but I don't think you need to do that. You see what I'm doing. And now we see what's left behind. Well, x plus 2 upstairs. And then, of course, downstairs, we have the 3x plus 4 and the x plus 1. And we are done. So what we're seeing here, and again, when you look at this kind of problem, you think, okay, well, you know, not too interesting. Truly, it's not very interesting, but you have lots of fractional expressions in science, engineering, mathematics. I mean, they're really the same. Science and physics and engineering, it's all math anyway. And so the idea is that it's good to practice these techniques. Right now, it seems a little bit dry and boring, and I will admit to that, but the techniques will be very useful later down the road. Now what we want to do is practice with some more fractional expressions. Just to get some more review, again, the main thing is invert and multiply. Now, when it comes to rationalizing the conjugate technique, I'll let you look at that in WebAssign, and you can check some of the SmartPen videos and things. There are plenty of examples there. I want to focus on things that maybe would be a little bit more difficult for you. So here we go. Let's do another simplify. So we have 2 times x to the minus 1 plus 2 times y to the minus 1 divided by 3 times x plus y to the minus 1. And what we're asked to do here is simplify. Now, you're thinking, this is kind of odd looking, Professor Ron. We got x's and y's. This is like a problem that you might see in multivariable calculus, because you got a function of 2 variables. And true, that is something you might see, but this is still an algebra problem that we can do. We don't have to be in a calculus course to do this. So WebAssign is just saying, okay, you're going to see some of these later down the road in its algebra, and I'm going to remind you how to do it. Now notice, we really have fractions here because these negative powers can all be written as fractions. And downstairs we have a fraction. So this is really what we call a complex fraction. That means a fraction of fractions. So first, what we're going to do is rewrite the, you're thinking, well, Professor Ron, could I do the factoring bit with the x minus the least power of x and the least power of y and do it like that? We certainly could. But that might be a little bit too much for you right now. I'll just stick with the x to the -1/2 and look at it that way. So to make this a little bit easier, I'm going to go back to rewriting these as fractions. But if you want to do that, you're certainly welcome to. I'm trying to give this to you in a way that you'll understand. But we could certainly do that. There are many ways to do a problem. You just make sure as you work the problem that you use legitimate techniques. If what you're doing you cannot justify by definition or a theorem, then don't do it. Work it in a way that you understand. And now, of course, here, so we've got 2 over x and 2 over y. And then, of course, x plus y we can take into the denominator too. So here is one way to look at this problem. Now, we have a fraction divided by a fraction, but notice this part right here is not combined. We really do need a common denominator to put everything together. So the first thing we're going to do is we're going to use the definition of division by a fraction. So we have 2 over x, and don't try to do every step at once. If you do that, you really will make a mistake. So invert this. So times x plus y over 3. Just work each step slowly, surely, with confidence. Don't try to do all the steps at once. Now this is fairly simple. It's good to go. Now here we just need a common denominator, and hopefully we can simplify this even more. So now we need a factor of x and we need a factor of y. So the least common denominator is xy. Now, just like we're adding numbers, we have an x here but no y. And then, of course, we've got a 2 common to all of this. I'll factor that later. So we have 2y. And, of course, here we have the y but no x, so we need the 2x. So now you can see that the y is absorbed to give us 2 over x, and here the x is absorbed to give us 2 over y. So we did that correctly. And now I'll just use parentheses, x plus y over 3. Now, when you look at this, you're thinking, okay, well, I've got a 2 common to both of these, so I'm going to say 2 times x plus y divided by xy. I'll use a little dot now, just mix and match. It's the same thing. And note we have two copies of the x plus y. So this will give us 2 times x plus y, quantity squared, divided by 3 times xy. Now, when you look at this and you think about this, you're like, okay, if I were in a class where I had a function of 2 variables, this would certainly be a lot easier to work with than that. So imagine that in calculus, you get an example or an expression after you differentiate or something, you do some technique, and you end up with something like this, or the problem is given to you and it looks like this. And the first thing you want to do is simplify it. So often you will find this in your science classes, especially in physics. Physics is always renowned for having formulas that are beautiful and elegant, but that's because they've been manipulated to be beautiful. And that's really what mathematicians do. You want your formulas to look nice. You want things to look easy. Even though it's not easy, you want them to be as user-friendly as you can make them. Now, here's another example that deals with negative powers that I think might be a little bit easier to do than maybe trying to do it with the last one. And this is a WebAssign. So here I want you to also simplify. So please take these problems seriously. A lot of students don't consider this important, but my friends, it's very important that you practice these techniques. So we have 7 minus 5x to the 1/2 power. So maybe I think in the book they call this using the quotient rule, and I could take some derivatives and show you, okay, this is what you get when you differentiate, but you'll get plenty of that in calculus. So say we differentiated and we got this expression. So in the numerator, we got 7 minus 5x to the 1/2 power plus 3/2 times x times 7 minus 5x to the negative 1/2 power, all divided by 7 minus 5x. So the idea here is we want to make this a little bit more user-friendly. Say we got this and we were interested in understanding if it had any zeros. And as we look at it, it seems a little bit hard to figure that out. Kind of like looking at this, when we look here, we simply understand it much more easily. So we could say that this expression would be 0 when x is equal to the negative of y, and that's very useful. So here, what we want to do is apply the same technique. That is, we want to extract the least power of 7 minus 5x, and then here, since we have a 1/2, get rid of that. So basically, we want to get rid of all the fractions. So we're going to say factor 7 minus 5x to the negative 1/2, the least power. And also factor the 1/2. We want to get rid of the fractions. The fractions are what make this complicated and make it harder to understand. So let's do that. So first, we've got the 1/2, and we have the 7 minus 5x to the negative 1/2. Now, I didn't dress these up like the last one, so we have to put our thinking caps on. Notice the minus 1/2 means that we have to adjust this to a 1 so that when we multiply back through, we get the 1/2 here. And of course, if I factor the 1/2 here, I've got to pay for it with a 2. So this will be 2 times 7 minus 5x. Now don't take my word for it. When you multiply back through, negative 1/2 plus 1 gives us a 1/2. And of course, 2 times the 1/2 just gives us the 1. So if you leave the 2 out here, then it's not correct. So this doesn't have the 1/2. So when you factor the 1/2, you have to pay for it. So again, just make sure that whatever factoring you do, that you can return to the previous expression exactly. Now here, what have we left out? Okay, well, we got the 1/2 and the negative power, but the 3 and the x stay behind. So we get that. So that's the hard part of the problem. So again, this is the same technique we did before, but now since we've done it before, we know what to expect. And then of course downstairs, don't forget about the 7 minus 5x. We often spend time worrying about the difficult part and then leave out the easy parts and wonder why the answer's wrong. Now, notice here we have a 1/2 and we got a negative 1/2 power of the 7 minus 5x, which we can bring into the denominator. So we have 2 times 7 minus 5x to the 1/2 times the 7 minus 5x. So again, here, this is 2 to the minus 1 essentially. So that's 2 in the denominator. And this is 7 minus 5x to the negative 1/2. So that's just 7 minus 5x to the 1/2 in the denominator, using the definition of the negative 1 power. Now up here, we just combine. So we have 2 times the 7, which is a 14. And we have 2 times the negative 5x, which is a negative 10x. And then we have plus a 3x. Now, what's interesting at this point is that all we have to do now is just clean it up. Let's combine the like terms. So we get what? 14 minus the 7x. And then downstairs we have a 2. But now, of course, that's a 1. So the 1 plus the 3/2 gives us 7 minus 5x to the 3/2. And we are done. So the idea here is we certainly use the power rules often. We saw in college algebra that the power rules and the exponent rules were virtually the same, that the exponential functions enjoyed the same type of power rule that the power functions did, and we use that. And then we see that the inverse of those functions, the logarithms, enjoy the same kind of manipulation, but as a power of the base. So all of these nice rules that we use make this kind of problem possible. And even though it takes a little bit of time to get used to factoring the negative power, look at the payoff. Look how clean it is. Again, you can get a common denominator and do that, but this accomplishes the same thing in the same amount of steps or fewer. And it's clean and it's easy to check. So very easy to check. Notice here, if we want to just use the fractions, we can do that too. It's always your choice. Legitimate steps will give you the same response. You don't have to worry about anything being incorrect as long as you use the proper techniques. And for a student in mathematics, you may have different techniques that accomplish the same goal. So keep that in mind. Now, what I want to do is to remind you that as you do your WebAssign, we'll basically be focusing on the factoring techniques and also this arithmetic with the fractions. Now, you're thinking, why are we so interested in this? When are we going to start solving some equations? Well, we're ready for it. Now, back in college algebra, you start the class basically by solving equations. But what's nice about this class with Dr. Stewart and his pre-calculus text, I think he gives you a better introduction to it. Now, what I want to do at this point is to focus on some results that allow us to take this algebra and move it forward. And I'm going to say a little bit more about why these are true, but basically I just want to summarize them and then use them in a few examples. Now, look at the first one. Remember, every time we factor an expression to arrive at a product, then solving equations is made much simpler. So this is a rule here. This is actually something we can prove. We call it the zero product. So, for instance, formally stated, if you just take two real expressions, or they could be complex too, but we're going to focus on the real expressions here. If we have a product, so we're thinking of A as being an expression and B as being an expression, and if that product is equal to 0, then it is true that at least one of the factors must be zero. So when you think about solving equations, your professor says, okay, set the factors to zero. Well, this is why. And you do this without thinking about it. So, for instance, when you look at what we've done here in these particular problems, if you look at this point here, we set this equal to zero. That means x would have to be the negative of y, or y the negative of x. Here, we can go one more step. Let's just go ahead and beat it to death. Let's factor, in this case, a -7. And that gives us an x minus a 2. You're thinking, let's just keep factoring. So let's go back to this. Now, for instance, if we set this to 0, we know that fractions are only 0 when the actual numerator is 0. Even though we have a product here, we've got a -7. This is never 0. But if this is actually equal to 0, that kind of we're doing the backwards argument, we have to say that the x minus 2 factor must be 0 if this is going to be 0. Of course, if that were just a constant, it wouldn't be true at all. So what we can see here is that when x is equal to 2, this is actually 0, and that gives us no problem in the denominator. So there are modifications that we'll have to do with the zero product law. But what we're seeing is that if we have factors that are multiplied and the actual product is set equal to 0, then we can use this law to move the problem forward. So what you want to write in your notes is, we'll say factoring. Factoring is essential. You don't factor because your professor just tells you to factor. You factor because it moves the solving of equation process forward very, very much in a way that puts you in the know. So the manipulations you do, factoring, combining terms, common denominators, absorbing common factors, allows you to use the zero product theorem. Now, two other theorems that I just want to remind you of basically help us to continue this process. That is the square root property. Now notice, if we have some real number a, and we have some variable expression x squared, it could be real or complex, we have x squared equal to a, then it is true that x is equal to plus or minus the square root of a. Now, what's interesting about this particular result, if you start with this, it's easy to get that. If you square the square root of a plus or minus, you're clearly going to get a. So that doesn't require much of a theorem. It's true in laws of exponents. But when you go in this direction, we can use a factoring method or use absolute value. Most students like to just think of this as factoring. So here's an idea that you can put in your notes here. We can say x squared equal a can be written as x squared minus a equals 0. So if we were thinking about going in this direction, we can now write the a as a perfect square. So we can say this is equivalent to x squared minus the square root of a quantity squared. Okay? So the idea here is that now we've introduced the identity for the difference of two squares. So now we can factor that. So this will be x minus the square root of a times x plus the square root of a equals 0. So when you see these results, most of the justifications are well within your reach. And so now you see this and you say, oh, we've got zero product. That is, we have the product of two expressions equals 0. So this will say that at least one of them must be 0. At least one of these factors must be 0. And so we look at this and say, okay, well, let's use the theorem if and only if x minus the square root of a equals 0, or x plus the square root of a equals 0. And so now when we solve this, we get x equals square root of a, or x equals the negative square root of a, and we're done. Now, the caveat here is that students always forget the negative. If you say x squared equals 25, x equals plus or minus 5, students will say, oh, the answer is 5. Well, maybe if you're restricting the solution set, fine, but you have to give me both. So this is a way to see that the square root property is valid just using factoring techniques and the difference of two squares. So you might say, well, that's kind of an interesting technique, Professor Ron. When you do calculus techniques, this is often something you have to do. And it helps you to write your expressions where you've got the zeros readily available. That is, we will do this again in this class, and we will find that this type of technique allows us to give a very clean equation where the zeros are very obvious. Okay, so I wanted to show you that just as a little aside. Now, one formula that I know that you've used, and here's another thing, ladies and gentlemen, put these on note cards. Put these on note cards with your identities. And write these down every day. And practice your WebAssign and use your note card to make the connection to the problem. That way you will more positively reinforce these techniques. If you say, I got it, it's easy, I'm not going to work hard with this, well then you won't get any better. So do practice this, even though you've seen this before, practice this like you have to go teach a friend to reinforce. Now, one of the types of techniques that we find to be essential, that is, we really like to factor. Professor Ron's lemma is very useful, but maybe we don't have rational zeros. Maybe when we try the AC lemma, we cannot find a z and a w. We can't find the z and the w that sum to the coefficient of the linear term, that is the b. We can't do it. So that theorem says, sorry, it's not going to factor in the rationals, so we've got to worry about another technique. That's called the quadratic formula. So let's suppose that we have an A, B, and a C that are real, just like we had in Professor Ron's lemma, but we set it equal to 0. So basically, what we're trying to do here is saying, what are the zeros if we can't factor this? This theorem says these are the zeros. So when you actually write your factored form, here's the formula for the zeros for this quadratic. Here, the square root property is simple because you have no linear term. That's a simple equation, but it's made more complicated here, especially when we can't use Professor Ron's lemma. And this is a theorem you learned in college algebra. That is, x will be the opposite of b plus or minus the square root of b squared minus 4ac divided by 2a. Now, a lot of you like this formula. You're thinking, I don't like to factor, so I like the quadratic formula. But I will say this, use the quadratic formula when it's essential, but always practice your factoring technique because factoring is also essential. It's not always the case that you need the zeros, you just need an expression that is more user-friendly to actually accomplish certain tasks in a problem. Now, before we actually talk about how we derive this, we want to use it a little bit. And I just want to remind you of a couple of things from your college algebra. Remember here, the b squared minus 4ac term, which is the argument of the radical, this is called the discriminant. So you remember that the discriminant tells you what types of solutions you're going to have. For instance, when we think of taking the square root of a real number, the discriminant could be 0. And if that were to happen, then this part of the problem goes away and we just have minus b over 2a. So that gives us two repeated real solutions. Now, if the b squared minus 4ac, that is the argument of the radicand, happens to be positive, then we get the plus or minus two distinct real solutions. Now, and this is something that we're going to spend more time on as we get to the theory of equations. If the discriminant b squared minus 4ac is actually less than 0, then by definition, the square root of a negative number is imaginary, and we get two complex conjugate solutions. So I want to remind you of this as we move through. Right now, we're just sticking to real solutions, but I want us to be aware that we actually can work this with the imaginary solutions. And that's what we find. Unfortunately, formulas past degree 2 are not helpful. They don't even exist past degree 5. Heinrich Abel and Évariste Galois actually proved these items. Those formulas are not possible, but the fact is that the formulas are so unwieldy that they're not even useful. So we're going to make the most out of the quadratic, and quadratic form and all of that will be something that we're very much interested in. So let's look at some examples here. Now, when you think about doing examples here, let's just look at some easy applications of the square root property. Say you're in a physics class, you're doing some kinematic equations, and you have something like this. Here's something I made up. So you have 3t minus 1, or plus 1, we'll just make plus 1, quantity squared, minus 36 equals 0. So what I've done is given you some user-friendly numbers. Now, when you look at this particular problem, the directions will be solve for real solutions. So say you're doing a WebAssign problem, and the directions are to find all real solutions. Now, when you look at this, you have an expression squared and you have a real number, but it is not in the form of the theorem. So the first thing we want to do is, and when you do solve an equation, you're actually doing a proof. I don't think students say they don't like proofs, but every time you solve an equation, you're actually doing a proof. So now we're going to say equivalently, we have 3t plus 1 quantity squared. So if you remember, we want to make the form look like this, where we have the squared expression equal to the number. So that's the next step. So let's do this. So now when we look at this, we have the form of the square root property. Remember, math is all about what? It's all about recognizing patterns and then utilizing our manipulation of algebra to take advantage of the patterns. Now, equivalently, square root property will have 3t plus 1 is equal to plus or minus the square root of 36. Now, students will try to get kind of fancy on Professor Ron and throw square roots all over the place. Don't do that. That is not how I've taught you. When you see this, this is the next result. Don't slap square roots on everything. That's not how I've taught you. This is equivalent to this. So now, if you like, we know that the square root of 36 is 6, so we can go ahead and simplify to plus or minus 6. Now, this is going to give us two solutions. So for the plus, we'll say first solution. We'll look at the plus radical. So we have 3t plus 1 equals 6. So this will be 3t. Subtract 1 from 6, we get 5. Divide by 3, 5/3. So that's the positive radical. Second solution. We'll do the negative radical. 3t plus 1 equals negative 6. Now, of course, I don't care if you go ahead and solve the equation further here and write it that way. It matters not. The main thing is this, ladies and gentlemen, that once you start interpreting things, that you use good mathematics. So at this point, we subtract 3t is equal to negative 6 minus 1, which is negative 7. Very simple Algebra 1 techniques. We need our Algebra 1 and our general math. Believe you me, when you do limits in calculus, you do a lot of arithmetic. So that general math comes in very handy. T equals -7/3. Now let's look back at this. We don't have any issues with undefined, that is division by 0. We look at this problem and say this is the square root property. And our theorem has told us that we have a solution t equal to 5/3 and a solution t equal to -7/3. Now WebAssign may say this. They'll say list the solution separated by a comma. And so we can do that, or we can just put them in curly braces. So I'll do a comma here. Now here's the thing, and I want to say this very emphatically. When you are asked to do a math problem, and the problem says solve this equation, you solve the equation and you are done. You do not approximate it unless the problem requests approximations. Otherwise, you are to assume the exact response. Ladies and gentlemen, I think because we live in a calculator age, that everybody thinks that the approximation is correct. It is not correct. We can use the approximation for other methods, for understanding our numbers a little bit better, to make them more user-friendly. But when we do mathematics and we do engineering and science, we want an exact response. Then we can manipulate that exact response to make some deductions. So when I finish my problem, I go into WebAssign and I type a fraction, 5/3. Or I could write it as 1 2/3, comma, and then I type a fraction, -7/3, or -2 2/3. Excuse me, -2 1/3. I can write an improper fraction. It doesn't matter, or I can write a mixed number. Give an exact response. So let me write this down. I'm going to put this in red. Exact responses. Exact responses are expected. I expect them. WebAssign expects them. I've taught a lot of students over the last 11 years at San Jacinto College, and the WebAssign has gotten them ready, and now they're engineers and mathematicians and computer scientists. So it does work. Exact responses. Unless otherwise directed. So you might have a problem, say you're doing an application with growth and decay, and they say round to the nearest whole number. You do your work exactly, and then you do an approximation because it was requested. Let me also say this. If you put a decimal and they don't tell you how to round, then how do you know what to do? So the idea is always, always give the exact response. Only give an approximation if requested. And if a number is given in a problem, you assume it to be exact. Okay, if a number is given to you in a problem, you work with it as an exact number and you don't round or do anything. The numbers that are given in the problem are assumed to be exact. Now let's look at another example where we can use our techniques. Now, one thing that's interesting here is that when it comes to working with the quadratic formula and it comes to working with completing the square, we want to think, well, what's the easiest way to solve a problem that has irrational zeros? You're thinking quadratic formula. But I want to just work an example where we complete the square as a prelude to appreciating the quadratic formula. So let's look at this. So we're going to say solve for real solutions. So here's what we do. Let's use x now. So we have 2x squared plus 3x minus 5. Now, when you look at this and you think about this, let me just, and we'll set this equal to 0. First, what I'm going to do is I'm going to look at the discriminant, b squared minus 4ac. And so we have a equals 2, b equals 3, and we have c equals negative 5. So this gives us 3 squared minus 4 times 2 times the negative 5. So note, we have the minus minus, so that's a plus, and we don't have any common factors, so we have 9 plus, and so we have an 8 times a 5, or a 40, and this is 49. I like to make up these problems because I like to test you. Now, I've looked at the discriminant here, and I have a question for you, and I want someone to answer this for me. Do I need the quadratic formula to solve this quadratic equation based on what I've done here? Anybody can answer. Answer, go ahead and chime in. Well, if you're a little bit shy, if I look at this and I go back to my formulas here, I computed the discriminant. I didn't even use Professor Ron's lemma, but look here. B squared minus 4ac is the argument here of the radical. And now we look at this and we see, oh, that's a perfect square. I can still use the quadratic formula, and we're going to use it, but what we're seeing is that we could have factored this using Professor Ron's lemma because that's a perfect square, okay? So that's one thing I want you to be aware of. So note, since, write this in red, since 49 equals 7 squared, we can factor to solve this equation. That is Professor Ron's lemma. And maybe you're working on a test and you're thinking, well, you know, it asked me to solve this equation. It doesn't really matter how I do it. And I completely agree with you. If I ask you to solve an equation, you can do it by any legitimate methods. But now I want to just go ahead and use the quadratic formula. So let's recall from the theorem, we have x equals the opposite of b plus or minus the square root of b squared minus 4ac divided by 2a. So let's fill this in. We've done all the dirty work. So notice here, this is positive. So the discriminant result says 2 distinct real solutions. So let's go ahead and fill everything in. So we go up to our b, the opposite of b, -3, plus or minus. Now we know that the square root of 49 is 7, so we have plus or minus 7. And then we have 2 times 2, which is 4. Now, this implies, or equivalently, we have a first solution, x equal -3 plus 7 over 4. So this is going to be a 4 over 4, or 1. And then we have x equals -3 minus 7 over 4. So this is a -10 over 4, which we can reduce to -5/2. Now, what I want to do is just to remind you of the other process, but now we can see the solution set. WebAssign says, list our solution separated by a comma. So we'll say 1 -5/2. So we're thinking, if I need the solutions to a quadratic equation, I'm not asked to factor, I can use the quadratic formula. Now, let's just say we were doing this problem, same problem, but I asked you to factor to solve it. And then you're keeping your fingers crossed thinking, well, I hope this factors. So 2x squared plus 3x minus 5. And notice when I do this problem, what does Professor Ron do first? You do the discriminant first to keep the arithmetic easy. Do the discriminant first. So now when we look at this, and we'll just say solve by factoring. When you become a math professor or a math teacher, you like to do problems several different ways. So let's look at AC. AC equals 2 times a negative 5. Well, we didn't hit the jackpot very well here because when I add those two numbers, I get negative 3. I need positive 3. So we're just going to move the negative over to the 2. Jackpot. Professor Ron's lemma says if you can do this, then this will actually factor in the rationals. So now let's go ahead and finish. So equivalently, we have 2x squared minus 2x. Let's rewrite the middle term. That's what Professor Ron's lemma allows us to do. So now again, the middle term is written as the sum of these two terms. So now we can factor the 2x from the first two, and we get an x minus a 1. And now we can factor the 5 from the last two and get the x minus 1. So now we can factor by grouping to finish. I like my document camera from Japan. I'm very pleased, and I look forward to using it to do some other things. So now we have x minus 1, which multiplies what? It multiplies 2x and a 5. The distributive law is our bread and butter. That's what factoring is all about. The distributive law and factoring are equivalent. Now, where are we? We're back to our friend, zero product. Zero product. So now, when we look at this, we're thinking we've got a product of two real expressions equals 0. So zero product says x minus 1 equals 0, or 2x plus 5 equals 0. Now, I will say this. The quadratic formula is nice and clean, and especially when you have rational zeros, it's pretty much required, or irrational zeros. But when I ask you to solve an equation, you can use whatever method you want. When I'm asking for solutions, your method, as long as it's legal and legitimate, is fine. So by solution of equations that are first degree, we're good at that. Add 1 to both sides. Now here, subtract 5 from both sides. Again, very basic mathematics. And then divide by 2. And so now our solution set 1, negative 5 halves. Now, what we do here, if we look at this and compare the two techniques, the amount of work is pretty much the same. Actually, this may be a little bit quicker, but what I'm pointing out here is that this is an additional test for factorization over the rationals. That is, if you just compute the discriminant and it's a perfect square, then you're done. But you're thinking, you know what, I've already done this, let me just finish it with the quadratic formula. Maybe that'll be quicker. We saw it was really fast. Again, like the square root property, we break it up into the plus and the minus radical and write out our solutions and then put them in a solution set. Now, when we compare this to the factoring method, about the same, maybe a little bit longer, but say we want to review the factoring method, so we don't compute the discriminant, we do Professor Ron's AC limit and we see, yeah, it will work. We can think of the Z as being -2, and we can think of the W as being 5, and there we have it. So what I want you to do is to be able to factor and to be able to have confidence in your factoring to prepare you for the calculus. Ladies and gentlemen, I've taught all the classes in linear algebra, differential equations, Cal 1, Cal 2, Cal 3. The amount of algebraic manipulation is ubiquitous. That is, it's all over the place. When I teach curve theory and theory of vector functions in Calculus 3, the students are astounded by all the algebra that you have to do just to compute curvature or to compute a T and B frame. It's really tedious work. And so what we want to do is be very comfortable with factoring, very comfortable with working with numbers. That's what gives us the power to do the problems we want. For instance, say you want to be an engineer for Verizon. That'd be a great job. You've got to learn your math so you can enjoy that great job improving communications throughout the world. And I'm a big fan of engineering. I think it's a great career. And you are certainly to be honored by the fact that you have stepped into a career path that will certainly help you make the world a better place. Now, here's what I want you to do for homework. I want you to review that last problem in 1.3 and go ahead and start working on 1.4 and 1.5. So what we're going to do is we're going to solve some more equations, and then we'll have some time to seep into some of the word problems that I know everybody likes. I know the time, rate, distance, fraction of work, mixture, not the most popular, but I'm going to show you some techniques that will make them easy and techniques that you can use to teach your friends to do. Now, another thing I want you to be aware of, don't worry about attendance. I have the report and I can do the attendance after that. And I will download, once the Sanjak sends me the copy of this, I will download this and have this on the Blackboard site, have a link so you can actually review our lectures throughout the term. If there are things that you want to hear again, that is certainly something that we will do for you. So one more stab at the Sanjak email. If your Sanjak email is fine and working, then you've done what I need you to do. Get your WebAssign set up. Everything is linked to Blackboard. Blackboard is your source of information for this class. So I want to thank you for attending class today. Pre-calculus is a beautiful, beautiful course. You learn so many great techniques for studying calculus. So I'm glad that you're here, and please make your math class one of your priorities, because as future STEM professionals, you will certainly have many occasions to study math, and you will certainly be required to do well in your math courses. And I want to help you to have that success. So I'll be sticking around, so you're free to leave. Again, thank you very much for attending today. And for right now, for the rest of the week, I will be having office hours, which I will do through email and WebAssign messaging. And hopefully by the end of the week, I'll have compiled a composite list of all my students' emails that are valid. I tried to do this on Sunday, and 10 to 15 of them were no good. And Outlook was telling me to delete all of them. I don't want to do that. So help me help you so I can send out invitations via Zoom to all of my students. I cannot send invitations by section. I need to be able to send to all of my students. So help me do that so we can have Zoom office hours. All right? You have a great day, and please stay safe. Thank you.
Thank you.
Thank you, dear. Have a good one.
You too. Bye.
Bye. chat messages.